Hey, so welcome to today's lecture on deep learning and neural networks. What we're planning today is that we are doing a bit of a different style of learning. Until now, we always had a training data set, which is hopefully very similar to our test data. We train on it, and that is then how we use it. The problem we'll see is that this is, yeah, often there's limited training data, especially if you have a very specific task. And on the other hand, neural networks are very good in learning some more general concepts, and we'll try to make use of that by, transferring knowledge from one task to another. It's hopefully a bit like you're doing it. I hope when you learn something in this lecture, you might apply it also to the other lectures. And also if you learn something in other lectures, you're using it here. And this is in traditional machine learning not the case. You have a specific test set. You're trying to learn that training set and then test it. But of course, it would be nice if you can learn more general concepts first and then be faster in learning there. And that's exactly what we want to look into today. For that, we'll first have a brief motivation. Then we'll look into a bit of related topic, which is domain adaptation, where the question is, what can you do if you have learned something and now you have a bit of a different distribution? So how can you then maybe learn the new type of distribution? Then we're doing transfer learning and looking mainly at three different points for transfer learning. Then on the one hand, on different architectures or choices which we are doing there. Then on what data we're fine-tuning, and then we're looking into the training, very briefly into the initial training, and mainly on the second part of the training. However, before we starting, just one short request. We're currently having, I showed you in the beginning of the lecture, the AI assistant or the lecture translator, where you can ask questions to the lecture, and I guess you might use that. You might also use a lot of other tools out there to help you understand that. If you're doing that, we would be, or especially one bachelor thesis author would be very happy if you could provide some feedback. So we did a questionnaire on here on what questions do you ask for a specific topic? And then maybe what answer did you get? What answer would you like to have? We have the link also in the slides. I can post there. If you can give us there some data where these tools are helpful and how they should be better, that would be very nice, and we can try to hopefully at some point build also better tools. But that is just side, so it would be really nice if you can give there some fill out the questionnaire is one question, so it shouldn't take too long. But yeah, didn't want to be too fast. So with this, let's start with the motivation and look on why we would be interested in doing transfer learning. Therefore, so the general setup we have until now is we do data collection. You think about it, gray architecture, and then we are training. However, if you're now tasked with a very specific problem, if you're somewhere and should solve something, then you have now a bit a contradiction. On the one hand, hopefully you have learned by now that, really great models, big models, large models, they're really cool. You can build really complex stuff with that. But in reality, if you work, you might have only very, very small data. So we have a bit of this very small data, but on the other hand, we want to use a very large model. And this is, of course, a challenge. We saw that with overfitting. So some of your data has to fit to how big your model is. And you cannot train a really huge model on a very small data set. So this is somehow challenging. And we have to see or look how we can address that we can build models which are really, really good, but we might have only very limited training data. If you want now to build a classifier which detects I don't know, laptops in an image you might collect. It might get 100. It will be difficult to collect like 1 million examples. And this is like often the case that, yeah, it's difficult to get these type of data. So the question is, what can we do, and can we somehow use other data or anything like that? Until now, there's also, if we're doing supervised learning and we're trying to minimize that, then we have to have some assumption that this type of learning normally works only well if this data is similar to the test data we have. Mathematical, it has to be drawn from the same distribution. So you have a single task, and if you're like train your models on like cats and dogs, if you then test it on images of human organs, it will not work. I mean, both are images somehow, but it's like completely different things. So it really has to be from the same distribution. And so this is a bit of, yeah, if we're doing this fully supervised, we're very fast hitting some border, because it's like difficult to really always get significant amounts of data. And it also seems to be a bit unnatural that we always have to learn everything from scratch. I mean, if you want to now build a classifier, which is very good in recognizing KIT buildings and saying, okay, this is the computer science building and this is that building, yes, you need some time to learn that. But as a human, you have already known how a building looks like, and you should be able to use this knowledge somehow. In this type of setup, we're not using that. We're training again completely from the beginning. And in neural networks, we have one thing which we haven't talked a lot about yet, but which is really, really interesting. And these are the hidden representations that are within the network. So we looked at very deep layers and so on, but what these also give us, that in each layer, we have these hidden activation of the image. So we always have in each layer like a mapping from like the input into an n-dimensional vector or a sequence of n-dimensional vectors or something like that. And it seems something is happening because these seem to be different, because if they would be all the same, shallow networks would be as good. So there seems to be some processing happening in there, and all of that are reasonable mappings, but they're different. And therefore, it might be good to have a look on what is really happening in these types of activations and what can we do. People especially did that like with smaller and initial networks, and one famous example is this data set where they investigate that on the MNIST data set, which is like recognizing digits. So there are single number handwritten numbers, and you maybe want to train a classifier. This is a 1, this is a 2, and so on. And then you can have a look at the hidden representation and to look how they are activated. And what they found out is that you're doing here some type of classifiers, some types of feature detectors. So whether there is a diagonal in there, or one feature is like whether there's a vertical bar. So what you're trying, what these different neurons in a layer also learn automatically without learning something which we traditionally did. So traditional vision, people looked at like feature detection and things like that. And these models seems to somehow automatically learn that. I mean, not like as always in this learning, not everything is interpretable, but in general, it seems to learn, like some layer seems to learn similar detection things, which also makes sense, because if you want to detect whether this is a digit or not, it might be good to recognize like what types of lines are drawn in the image. And that is somehow automatically happening. You look at the weights, and then you see how these weights are getting activated, and you see, oh, this weight is very high if there is a line in this one, or if there's a line in some other way. So motivated by that, what is really happening is that these networks internally learn some like feature detectors, which find things which are happening on the image, and then maybe on higher levels try to combine them more. They see that there's this type of line and then another line, up there, then it might be a 2 or something like that. So they're trying to, I mean, of course, again, it's not everything like rule-based. There's probability around that, but it's doing this type of feature representation. So if we're able to learn these types of features on in some layers, which are very similar and motivated or happening in other machine learning things. And what we did there is you hand define these features, and then you use these features for many, many, many other tasks. So maybe that is here also possible that we are training the network on one task, and then we are learning some type of feature representations here. And then if we're learning a new task, maybe we don't have to retrain everything, or at least not randomly retrain everything. But we can start with the one thing here, and then only learn change a bit up there to get the new task. So again, motivated by, if you think about recognizing KIT buildings, maybe if you already know how buildings are recognized, then it's a lot easier to determine which KIT building that is, because you know how buildings are different and what is a building and what not. So hopefully you have learned this in the lower layers, and then you have to learn a lot less. So if you mainly have to train only the top layer, you of course need a lot less data. So you can be more efficient, but still get the power of the big network, because this one was trained on a lot of other data, which you might have for some other reasons, which is not exactly this type of task data. And exactly that's what we want to look at. So can we do this type of transfer? So can we transfer knowledge that we have gained in one task and then use this transfer somewhere else? Can we transfer this features detection mechanism that we have learned in the one task to the other task and then learn faster this new tasks? We're going through the next part. We look at a first example and already the main algorithm. Any questions? Yes?
The reuse can be seen as pre-trained.
Yes, I mean, that is, I mean, if you do pre-training, that's mainly you do, it's like some other formula, you do transfer learning, you pre-train on some task. We'll come to in pre-training, at least typically what you assume is the first task is not a real task, but a self-supervised task, which you invent some task to get a basic understanding, and then you're doing that. But that's exactly where it's happening, where you use transfer learning. Before we're now really going into transfer learning, let's do a bit of a simplification. And domain adaptation is a bit of this case, but with a simplification, then it's exactly the same task. It's only that the data distribution is a bit different. So in text, for example, in machine translation, you're training a system which translates very good as news text. If you then use it to translate university lectures, might not work that well. The input is different. Or an ASR system, if it's very good at recognizing long presentations, if you then want to do it to give a heated discussion where people interrupt each other, won't work that well. So for vision, we had that if it's recognizing some type of images, others not. So in this case, the nice thing is, we don't have to really change anything in the model. It's exactly the same model, whereas the same outputs is only like the distribution of the output is different and the distribution of the input is also different. So how can we do like this type of domain adaptation? And in domain adaptation, typically we have this case, we have a lot of data in some initial domain where we can train on, but we're interested in a specific domain, and there it's hard to get data. And then it makes sense to do domain adaptation, where you first train on the large data where you have a lot, and then you transfer the knowledge to the similar domain. Just this time, it's not a new task, it's exactly the same task. And again, the very cool thing about neural networks because of that is, this is very, very easy. What we just do is, we are training our model on all the initial data we have, on the data which doesn't fit so good, but it's learning some very general knowledge about that. And then we're continuing training. The only thing is we are switching the training data now. So instead of continuing on this big bunch of out-of-domain data, we are going to the in-domain data and continue training there. Because then again, we're not shifting our loss function to be good for these examples and no longer for the initial. We have learned generally good knowledge on the out-of-domain data and now switching to the other one. So this type of domain adaptation, which is then called often fine-tuning, is super successful, very easy, and what you nowadays still in a lot of networks always do. And so it's somehow the basic technique when you want to like specialize a model on a very specific data set. So how did that work? And as I said, the implementation is really quite simple. You have your initial data. So you're training first on our initial data, where we always do we do the forward pass, calculate the error, backward pass, and update our thing. So it's a normal gradient descent. And when we're doing that, we're going over our training data. So let's assume now this is somehow randomly ordered. So we take first this first batch, then we're taking the second batch, and this way we're iterating through all our training data. And then we can start again and go through that maybe several times through that. And this is now, our general data where we have a lot of data. Now, maybe you're not super interested in how good you are in this general data, but you're mostly interested in how good you're on very specific use case. You want to be very good at recording these lectures in neural network, and that is most important. If you are not so good on all the other things outside there, is not so important. What you can do then there is straightforward. You have your additional training data, much smaller, but it's like really fitting to your test case. And now fine-tuning is you're just doing exactly the same thing. You're again doing forward pass, measuring the error, backward pass, and updating your weights. So you're going through this data again, but now you're going through this small in-domain data, and you're fine-tuning the model on there and doing that all the time. So this is the default thing to do in domain adaptation initially. And we'll see it's also like how we do transfer learning. In transfer learning, it's a bit more general because it can be a different task. So some things might be more difficult. We will see that, not everything is as easy, but it is one, very nice thing in this idea of gradient descent. If we're having other data, we can just optimize on that data and continue to learn there, and then get really good on this type of data. Good. Any questions to fine-tuning? So this is really the most important for that. Seems simple. It is simple, but everything else now tries to build upon that. You can make it better, but this is the initial idea, and it's essential for all type of neural networks, I would say, that you are training until now, because you're often not, as we did until now, that you train from an random initialized model, but nowadays you often start from training one model which has been trained on something like that. Good. With this, okay, then now extend that a bit to more general setup of transfer learning. What we're doing there is mainly exactly the same step. So what we have is we have our initial model, we have our initial data, and then we are doing our first step training. The initial training often will be pre-training called or something like that. And we'll talk a lot more about that today. We'll shortly mention meta-learning. After the break, we'll have a full lecture on self-supervised learning where people really look, how can we be most efficient there and really learn a very strong initial model. And maybe for the initial model, it's not important to be really good. It's like, for example, it should be a good feature detector and so on. Then we have to maybe transfer this model a bit to our final. We add our task-specific data in here. We're doing the fine-tuning, and then we hopefully get our final model in there and can then do the final model in there. So let's do some more details on the individual steps. So the first thing is the creation of your initial model. So if you're not doing transfer learning, what you will do is your initial model is randomly initialized. So that we don't want to do anymore, because then you really have to learn everything with our initial data, with our task-specific data, and the initial data is typically much larger as the other one. So we can do this as a supervised learning with a lot of data. Especially, for example, in vision, there exists really large data set when people have trained very large models in a supervised fashion. There is the other idea, and then people often refer, as was said, to pre-training, is you can train this one in a bit of an unsupervised way. So we know typically it's very hard to train a model or like to get supervised data. So if we can't get supervised data that easy, maybe we can make artificial supervised data, and that is why you're doing self-supervised learning, and that we're doing later. Another thing is you can, of course, now train the model not to be best on this data because you're not really caring about this data, but you can more optimize it in a way that it's afterwards easy to learn new tasks. That's why like meta learning is sometimes called learn to learn, so that you are learning a model that is then easy to learn a new task after that. Then we have the next step, which is we need to adapt the model to the new task. And that is now a bit different to what we are when we're talking about domain adaptation. So we want to be more extreme. It shouldn't be the same task. It can be a quite different task. We only want to take some part of the model and then use it also for the other part. So we might need to change our architecture in some way, or yeah, but of course we want to keep a bit what the model is because that is where things were helpful. And yeah, I mean, for example, the easiest thing is if you have some type of classification task here or sequence labeling task where you have a classification head at the top, that would be the easiest thing, that you change the top to the classification head, and everything below you copy over from left to right. And now you're not longer doing, for example, if you're about text, you've learned maybe named entity recognition, and then you're doing here slot filling or some related type. And what you're mainly transferring is all the knowledge you have. What was important to say these tasks, to solve these tasks, you're copying over because you're keeping the parameters, but the upper one is kept. It even sometimes works the other way around. So I mean, this is maybe more intuitive if you're removing the top, but it's a bit more difficult, but it's also working that you're even removing some parts on the bottom. So you, for example, you train a model on English because you have a lot of data in English, and then you want to fast learn it to German. You can also use this transfer, but of course, if you change something down here, it's a bit more difficult because then you first have to learn to map somehow in the same space as you did initially with the other model. And then, for example, if you do a new task, you have to adapt your classification head, because before you had n classes, n1 classes, now you have n classes, and then you're doing here your new classification head that is able then to do the right time of predictions. So if you had before a model which takes images and has like 3 different output classes, can do cats, dogs, and mice or so, and now you want to use it to classify flowers, then you might have now 5 new flowers to do the new classes, but maybe some initial features like how to recognize things in the image was helpful, and that's why it's good to only change the head and like first keep the other one. Wait, keep it. I mean, of course, you might not. That doesn't mean that everything else is not changed. We'll come to that. It's not like if you only change the head, that you only change the head and the rest is now frozen and never will change. You might also change that, but at least the idea this is a better starting point than just randomly choosing weights in. Maybe it's more surprising that randomly choosing something even works so well as a good starting point. Good, and then we're coming to the final step, and that is now the transfer learning, so the creation of the final task. And there's like different versions of that. So now the question is it the same task? Then we said it's domain adaptation. It's a different task. People normally call it transfer learning. Can also be that you're not wanting to do it to one task, but to many tasks. Again, that all mainly says in the last step, you also want to gain from not only having one task, but you can, of course, not only do it like one after the other. It might also be beneficial to learn several things in parallel. So you can also, in the last step, in your task data, not only have one task, but have several tasks. So for example, maybe it's easier if you have a multilingual model, it's learning better if it's not learning only one language, but 5 or 6 languages. So you can do there also then you did. And then one question we're coming to that is, do you have access to the training data of the initial step that is sometimes helpful, or you don't have access? Do you just continue learning, or do you have still access to the data and maybe can use it again? So that seems to now we have a basic idea. So the first question is then everything solved? Can you imagine what might be difficult when doing this type of transfer learning? Any ideas? Even maybe for you as humans are a lot better at that. Or what happens sometimes if we learn something new?
Maybe you forget the old stuff.
Yes, and maybe that's not always bad. Sometimes you want to forget, but sometimes this is also not what you really want. And while this fine-tuning is very efficient, so we can very good learn new things, it comes also at the cost that it's very efficient in deleting what you learned before. So you're sometimes too fast unlearning, especially if you want to have a model which maybe can do also the things before. So here is an example. There it was done for automatic speech recognition. Imagine you're first learning to recognize some other languages, and then afterwards you're learning 5 new languages. So you see here previously it was 10 languages, that's the blue one, and then new languages, even more were added. This is Oracle. This is if you have access to all the data and train them at once, you're very nice. The problem is if you now this transfer learning, you first learn all the other languages and then you add languages. Now, of course, the question is, if your only goal is to be good at the new languages, oh, you're quite good. Not as good, but nearly as good, like 17. But you really got bad on all the other languages. So it's very fast in unlearning things. So maybe we want to prevent that because maybe our new data, I mean, of course you could say, yeah, the new data, why do you care about the others? Typically, the new data is very small. So you might even then go on to strong overfitting and you want to prevent that you get good at that, but maybe the data is not exactly as your training data. So you should still have some abilities to generalize. And that is typically a big challenge in this type of transfer learning. And therefore, we want to investigate several techniques in order to make this general setup of transfer learning very key. So we train on one task, change the model, and fine-tune on the other. And that's the basic transfer learning pipeline, straightforward. But in order to address this type of catastrophic forgetting, we look at what we can do different in the what we can do different on the side of the models of the architecture. We'll especially look at again at like some changes in the architecture so that we more specific define what we want to learn or not. We'll very briefly look at, and this is like then we're talking about adapters, which is somehow the standard thing now. If there is a thesis and you're writing and you want to build a model, adapters is like the important stuff because that's like how you fine-tune or transfer knowledge of a big pre-trained models into a very, very specific small task. Then we're talking about, maybe to reuse some data, replay, and then a bit more about training, how to train the initial model, how to fine-tune it. Maybe you want to minimize the changes or explicitly learn how to like learn things and use things and not remove what you have learned before. Good. So let's start with the architectures and see what is possible there. So let's assume we have that like a sequence labeling problem. So you have here your words as inputs in one hot encoding, make continuous vector out of that, and then you have an RNN or self-attention or state space models in there, and then you do your predictions out there. And the first thing you could do is, yeah, maybe it's a good thing to at least learn this mapping, like how to map a word to a continuous vector. Seems to be very task independent. So independent of whether you want to find out names, whether you want to write summaries, or whether you want to find the part of speech text or anything. Like have a good representation of the word seems to be a very basic thing which you might want to always do. So the first thing is and that was also like the first thing people did is like this mapping from the one hot encoding to a continuous thing is called what people call the word embedding, and so you can use them and reuse them for your task. If you now look at this image, you'll think, okay, this is like a really, really minimal type of sharing between the models. So you train the embeddings on one model, and then you build a full network on top of that for the other task. What is your impression? Is that like from the number of parameters, is that really small or is it big or?
Normally, the most parameters sit in the embedding.
Exactly. So this is typically already a lot of parameters. Why? Let's have a look. So what you have typically is you start with a word. When you have then like words, maybe 50,000 words, we have to say we always use one hot encoding. And you might go to 250 hidden dimension. Then you have here around 12 million parameters just in the first embedding layer. Just because it's like a matrix, or you can also think you learn one 250-dimensional vector for every word, or you can learn the matrix, which you multiply with the one-hot vector, get that exactly the same. This matrix has to say the size 50,000 times 250. So this is quite big. If you then look at the LSTM, you're now down to the dimension. The problem is that you start with your one hot encoding in a really huge dimension. So here it's like only 250 times 250, which is roughly 500,000. And then here it's only if you're on the top where you go to a classification with 10 classes, it's only like 2,000 parameters or something. So here is really where most of the parameters are. So if you can already do that, you have transferred a lot already, because you have learned this representation of for each word, which is only like 250 dimensions, and there's already a lot of knowledge encoded. So even if you're doing that, you have now a lot less parameters. So instead of like 12 million parameters, you only have 500,000 or 3 million if you have 6 layers. But even if you have 6 layers, you're like 1/4 of the parameters you initially had. The other extreme case first is that you can do somehow the maximal sharing, which means that you're just replacing up here your classification head. And then instead of, for example, predicting here the next word, you're now predicting here the labels. So that is the minimal one you have to change, because we have a different, typically if you have a new task, you'll have a different set of labels. So that one you would change, and the other ones you might keep even fixed. So you're not allowed to do that. So that change that. So that is like the one techniques in order to limit the parameters you learn and to limit overfitting, that you what we call freeze. So when you do the optimization, you're not changing all parameters anymore, but you freeze these parameters here in red and only allow to change the orange ones. The nice thing is, of course, you can freeze by just not updating your gradients. The nice thing is, if your gradients, if there's nothing updating below anymore, you can stop calculating even the gradients. So if you do that, you only have to do the backpropagation like one layer down. So it's also a lot more efficient, like computation-wise, because you don't have to do the full backward pass. You don't have to store all this one. You only have to store them for the upper layer, and then you're done. So yeah, the first one is like looking at your architecture and checking which parameters do I want to update. The default was maybe everything. Now you can say, oh, I can copy over. So there's two steps, to be honest. So one is which parameters do I use to initialize? And then the next question is which parameters I allowed to update later. They don't need to be the same, but of course there's a very strong dependent on each other. Any idea? Not all combinations make sense.
It doesn't make sense to don't update the parameters that we initialize randomly.
Exactly. So that normally there's some weird version where this is even somehow working, but the normal thing is not. So normally you should either like keep the parameters and freeze them, keep the parameters and update them, or randomly initialize them and update them. But randomly initializing and then freezing doesn't really make sense there. Because I mean you want to keep what you have learned in there. However, there is now also like a third way where you allow for allow the model that it's not only has to change all, but you're mainly freezing the full network, but then you're learning some minimal changes to it. So like somehow in between that you're not allowing everything to change, but you add some new parameters and only learn these type of new parameters. And that is what is called adapters. So they're in each type of layer. That's now, of course, always depending. And you can, like, again, decide, like in normal architecture, do I want to add adapters everywhere or only at some point? But the idea with adapters is that you're now in your network, you add new components, and then these new components can be learned so that you maybe can learn to modify your original hidden representation a bit so that they better fit your task. But you want to modify them at one thing at different positions, because at different positions you learn different things. So you don't want to like only learn at the top, because maybe there your initial, if you want to have a different feature detector, because now maybe it's more important that it's green or red and no longer that it's blue or yellow, and maybe it makes more sense to learn this further down. But you don't want to change everything. And that is possible with these adapters, which you put in between layers, and that can be any type of layers. Again, all these types of layers we have, and then you have the ability to learn their more things. And that's what we want to look now more, this idea of learning task-specific knowledge at each task, which is called the adapter. So let's start with the baseline. So what is the baseline? We have a layer which does a lot of calculation, and then this layer generates our hidden representation. That's the output of the layer I, and we use that then as input to the next layer. And then the layer does some type of calculation on top of that, and will generate, therefore, the next type of output up there. So this is one way of doing it. Now you can add different types of adapters to that. The main idea is now maybe you want to learn that, I mean, you don't want to change the full layer because that's a lot of parameters. Or maybe you want to learn that, yeah, you have to change the parameters a bit. For this task, you have to interpret things a bit different. And that's why we mainly want to jump in on the different points and find what we're changing there in order to make a better learn a better representation. And there's two ways of how you can do that. There is so-called serial combination, where we add an adapter between the layers, mainly like that. So you have your hidden representation, but you're not putting this representation really in the next layer. In between, you have a new, like, small neural network, which you add, and then you're putting that into the next layer. Not surprisingly, if we're calling this one serial adapter, there might be another one, and that might be called parallel adapter, and it's also quite reasonable. So instead of like, what we can also do is like, instead we're just going in parallel to this layer, and instead of this calculation, we make maybe also another calculation and add them there. Does it look a bit similar, the picture, to something else?
Looks a lot like the residual connections with evenly on top of our.
Yes, exactly. So we have a bit like a residual connection, but the important difference is we're not doing a one-to-one mapping here. So we're learning something to change there in there. Again, the idea is, yeah, you mainly want to learn the delta. So yeah, you have solved the one task, but in order to now understand the other task, what do you have to learn differently? And in order to prevent the model from unlearning everything here, what you're doing is, oh, can I just learn only the new thing and not unlearn everything what I had done there before? Good. So how can we do that? Let's go a bit into the more details, and let's start with a serial adapter. So what we have is we have as input here hidden state. We want to get a new hidden state as output. Now I just assumed here that these two hidden states are the same size. So both have the size n. Why did I assume that? Is that a good assumption? Yes?
Was if I expect here as input size, the output size player.
Exactly. So that's how it's trained, and we add the adapter later. So we can't now change this and like, oh, I mean the adapter I plus one assuming n as input. So we can't change that. So the adapter has to be like somehow a mapping, a one-to-one mapping, which doesn't change the size of the vectors. And then how an adapter looks like, I mean, that you should know by now, is a very easy feed-forward neural network. So what you can do is just you take a parameters W, multiply it, and then with a do nonlinearity there. So you mainly have an additional feed-forward layer there, which you're training. Seems to be very easy. Is it reasonable? Is it a good idea? Or do you see any problems? Yes?
Well, I expected to still unlearn things that it learned initially, because it's going to change the values and weight a little bit, or more likely input to the next layer. So it won't be able to recognize exactly like it was before. While parallel, I would expect to learn new things and still keep what it's already learned.
I mean, yeah, it's changing the model, but that's happening with adapters. I mean, if you randomly initialize that, yes. If you're more initial that maybe in a diagonal, it would start at least as very similar. And so it might be possible, but I mean, that's in general, of course, a problem. But also, if you do add adapters, even the best ones, often you first see a drop in performance because you're just disturbing things, and that's what the models are sensitive to. But normally you can recover that at some point. So I think that is recoverable. But there was another idea.
I think if you have a completely new network between two layers, you increase the size enormous.
Yes, I mean, that is a bit of a problem here. You're not really adding that few parameters. So if you're again thinking that your hidden size here maybe is 1,000, then you have 1 million new parameters. So if your layer I is a feed-forward network, you just add another full layer in there. So it doesn't really make a difference if I train layer I or if I train layer the adapter. I mean, if you have more complex layer, maybe, but still, it seems to be a lot of parameters in there. So that's not really what we thought about efficiency. So this is a bit like, yeah, the problem is for just doing that, because these sizes are so big, because our initial model is normally big, because you have a big model, if we're just adding an adapter there, that is not efficient and we can't learn that good. So we have to do something, yeah, a bit different in doing that. And there is a nice idea to that, which is maybe a bit counterintuitive first. If we split up the adapters into two matrices, we can make the joint of the two matrices a lot smaller than the overall one big matrix. And that's what people refer to as the up and down projection. So what you're mainly doing is you define an initial intermediate hidden size, which can be a lot smaller. So for example, you only go to 100. And then what you're doing is instead of having one projection, you first have a down projection, which down projects your large representation to a smaller one, and then you have an up projection, which goes from your up to from your smaller one again to your up. And the interesting thing is now, although you have now two layers, you have a lot less parameters. So if you're doing, I mean, of course, depending on your choice, but if you have, like, let's say, your hidden dimension is 1000, you go down to a hidden size of 100. That means each of these metrics is 100 times 1000 is 100,000. With 2, it's 200,000. So now you only have 1/5 of your parameters. So instead of training 1 million parameters, you only train 0.2 million parameters. So you reduce the number of parameters by a factor of 5, which seems to be nice. So there it's straight, and you're very free to choose. I mean, you can make the middle size here larger and smaller, and thereby reduce your parameters. So this seems to be nice, but so we solved the problem in that way that we have no few parameters to train, but there might be still a problem. Does anybody have an idea? Yes.
Information could be lost because it's transferred to a smaller.
Yes, exactly. So if we now think about information, I mean, in order to go from here to here, the information has to be encoded here, but they also have to be encoded here in our H dash, which is here, and then again here and here. There can't be information somehow added somewhere. So all the information which we have here in 1000 dimension has to now go to the 100 dimension. And that is, of course, might not be the best way to do it, because maybe we're losing now a lot of information and we can't use that anymore. So still not the right idea. So any other idea of how we can solve this issue? How can we prevent that we really have to put all the information through this bottleneck? Yes?
Maybe we can just add the initial hidden representation to what we get after the up-down conversion.
Yes, exactly. We know that from, that's called a residual connection. So what we can do just to say, oh, our hidden state is the up-down projection plus our original hidden state. So, and it's even intuitively a lot more logical. What now adapter learns is no longer it's learning to map the hidden state, but what it's really learning is, okay, how should I change the hidden state? So with this residual connection, you add mainly, okay, I don't want to learn really a mapping of the hidden state. I only want to learn like what things do I have to change in the hidden state. And now all information can flow around here. And this bottleneck is only limiting how much changes we can do to the hidden state. And there we might need a lot less data. We're not simply lost information. We are not somewhere completely different. So we only want to learn what is different, what new things do we have to learn, and that might be quite small. Good. Any more questions? Then we can go to the other adapters, and they are mainly now famous under the name LoRa, low-ranked adapters, and the somehow standard that we are having. What they try to directly address on the feed-forward layer, so apply to the different matrices. And again, you can apply that then to all different matrices, because we've seen in all the layers you have matrices. You can add LoRa adapters to your query key and value and self-attention, to the different matrices used in RNN and so on. So you can apply that everywhere. Just what mainly works now or looks at the part where you do a matrix multiplication. So what we're doing there, the new hidden state is the weight matrix times our hidden state. And now we're trying to do this parallel by saying, yes, if we're learning now, what we want to do is we're taking our new hidden state, but the new hidden state is the weight matrix of HI plus some delta matrix delta Y, and then we're applying that to our matrix, and then adding these two up. So you in parallel have your original one and you have your new one, and apply that to that. And here you again have the problem, of course, now that your delta W, how it's now called here, can be very, 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 very large. So that in this case, if we're just doing the formulation as before, we again have the problem that the W, the delta W have to have exactly the same form, because otherwise the summation doesn't work. So also here we have to look how we can address that. Yeah, we can handle the case that maybe these twos are not exactly the same. And again, we're doing mainly the same. So what we're doing is we're again doing a up and down sampling and replacing our delta W by just two matrices. So we have now the matrix A and B, where we are taking HI, we're multiplying it with B. Then this one has a lot smaller. We're multiplying it with B. Yes, B has a lot smaller dimension. It only has an D, and then we are upscaling it again to have a higher dimension. And this in LoRa, this is typically done by having B initialized with 0 here, and then A as a normal distribution. So this is what people nowadays refer as LoRa, where they look at the different matrices in your neural network, and for some of them, for all of them, then part of the definition, you're replacing this matrix, or you're adding in parallel your LoRa adapters, which can then learn, okay, what do I have to do differently than the others in this new type of task. And again, by having the rank, which is mainly the size of your intermediate representation here, you can then, of course, define how much you can change. Is it a lot or is it smaller? How much parameters do you have? And here you clearly also see that, of course, since you're doing your normal calculation here, it doesn't matter and it works. You're not losing anything. So you're not reducing the expressibility of your network at all. A different way of viewing on that is you can also view it more as a matrix factorization. So you are generally factorizing your matrix. So saying that originally we have our output is WS times X. Now we're replacing WX by WS times WM plus WB. So in this type of view, you even have more options. You have not only multiplicative, not only additive things like here, but you can also learn a multiplicative matrix that you're even allowed to change your original weights in a more multiplicative way, and then use this one extend. And again, this one is shared, and this one we have only for tasks. Again, if we don't do upsampling, we would have the problem. Now we would even double our parameters, but that can be addressed by parameter efficient matrix representation. So the most efficient one is if you represent your matrix just by two vectors, and if you multiply them in the wrong way, you're not getting, I mean, if you do a multiplication of a orthogonal vector and a horizontal, you get only one value, but if you switch it and you do a orthogonal one and a horizontal one in this way, then you get a full matrix. So with this type of multiplication, you can then get out of just two n parameters, you get n times n matrix, which you can then use. And then would be rank 1. If you want to have more ranks, you can just sum several of these and then get as many parameters as you want. Good. So these are adapters. Or we're going to the next part. Any more questions? So as I said, so that is nowadays, if you change your model, like a really big one, if you take Llama, like a big pre-trained language model and want to adapt it, like using adapters is somehow the default approach because you never will have enough data to really do a full fine-tuning. So normally the default approach is to use some type of adapters and then like only adapt like the model with limited freedom in order to be more efficient on doing that. Then we said if we want to be good in the type of learning that we're doing, another challenge is that we might unlearn our data that we initially have. And in some situations, we can address this by not only fine-tuning on the new data, but in what people call replay or mixing, where they are just always keeping some data from your initial model also and continue training on that. And of course, only possible if that's somehow possible with your model, or they have to have then two versions of the model with a different task which share some part of the network. But by doing that, you can prevent the model from unlearning that. So what you're doing is that you're not only looking at your initial data, but you're looking like you're switching between these two and sometimes taking from this data, sometimes from that. Of course, not always possible with everything. If you want to do that for a large language model, that's typically not possible because they will only provide you with the weights, but not with all your training data. But in a lot of scenarios, it's possible to have different data sets. Of course, this comes with one additional challenge. Anybody sees the challenge which you could have by having this type of replay? Or mixing. Maybe if you call it mixing, it's easier to see the challenge. Yes?
Maybe the initial data has a different format than the specific data.
Yes. Yeah, of course you have to bring everything to the same format. Yeah, but I don't think that is a major issue. Yeah.
The amount of how often the initial data is used because the quantity of increase is way higher. So the probability would be higher by default if not adapted.
Yes, so you have to somehow find weights on like how often you look at this and how often you look at that. And if you add more and more different data sources, things get, of course, more complicated. So what is the best mixture of your data is then a significant problem which cannot be like easily solved. I mean, until 2 or 3, you can just by hand define it. Luckily, often taking a 1-to-1 mixture is a very good solution. But that, of course, might get challenging if you have very different types of data sources and want to combine them. Good. And yeah, with this, then let's go for the last part of today and have a bit look at the training. So what can you now do during training? We have mainly 2 training phases. Although I have to say that is a bit of a simplification. Can you imagine how you can have more than 2 training phases?
Let's say you have, for example, a seen in the beginning that you pre-train really good feature detection, then you train the main model on all the data to do some easy understanding tasks, and then you have a specialization of that model.
Exactly. So this, I mean, the two-step approach as we do it now is like the first idea, but of course your initial model can already be trained on several steps. And as I said, so we're not limiting to two. Normally you're not getting like queues of like 100 different steps, but it might be in a lot of situations, as you said, that you can have 2, 3 or more steps to do. But in general, you have the main difference is you have the final one, which you're really interested in, and there you want to be good, and you have some initial ones. And for the initial ones, we'll talk later about how to use self-supervised learning, so doing a really completely different task. Today, we want to at least get the idea. We're not doing the very details. There's a lot more about meta learning, but at least a bit of idea behind that. And then in fine-tuning, what you can also do is now we try to limit the changes by having the architecture or like adding specific specificities in the architecture, whether freezing things is part of the architecture or loss function, I'm not sure. Also doesn't really matter that much. But of course, you can also try to do that by the loss function. You can try to add a term which tells you, oh, please stay as similar to your original model as possible. And that's what we then want to look in the second part. So let's start with the meta learning. The idea here is that we want to learn a model that is then able to fast learn a new task. So that is especially the case where we're having a lot of tasks. They're typically very related. So for example, here you have provision like classification tasks, and you're doing like just a very different subset of, so they're very related. So here you have like 5 different labels and you want to learn how to classify them. And then you have a test set which can do be a dog or piano, and you have these 5 different labels. Then you have another training set where you have these 5 objects and want to identify which one is this. So now in your training data, one sample is no longer like one point, but one sample, you think of this as a task. So this is one task, this is another task, and so on. And the question is, can you now build a model so that you can look only at very few examples and then solve the task good, so that you very fast can learn the new task. And that is the idea. And then you can testing by giving new tasks. So you give in new examples, and then it should be very fast in like learning how to use these samples to train the new one. So mainly you're putting your first and your second step, you're putting the second step into the objective to learn your initial model. You want to learn the initial model so that you can then fast learn the next thing. And that's why it's also called like learning to learn as an idea. So the main idea is that meta learning, of course, you can also do for other types of machine learning by neural network, is that we want to learn features that enable to fast learn. So what are important features? We have done that automatically in some way, but can we explicitly force the model to learn features so that it's easy to learn the new task? You can also phrase it that it's a fine-tunable model. So it's a model where it's very easy to fine-tune it so that you get like very good results. And the nice thing is you can formalize that in some way. So what you want to do is that you want to optimize your generic parameters so that the loss function, you calculate that you have some parameters and you use your test set, and then the loss should be small. And the loss is calculated based on this task-specific model. So the idea is you take your initial model, and then how good these parameters are depends on, if you take these ones, fine-tune them on your training data, DTR, how good are they then this generated model on the test data? that is the overall idea. So here you have, so from your training data, you have in your training data the split of training data and test data samples. The green ones and the red ones here. What your loss mainly says is now, how good is the model which is further trained on the training data given then on the test data? The question is, how do we train this one? How would you train a model? So how do you do your second step, the training of the model of the task-specific model? Maybe it's too simple. What did we now learn? What is the best way to find it? Oh, I said it now. Okay, we're fine-tuning it, of course. So fine-tuning is very easy. What we're doing is we're taking the initial parameters, we're calculating the loss with respect to our training data, and that is then our fine-tuned model. And we can do that maybe for one step or some steps, and so on. The nice thing is now that these steps are again differentiable, like these updates themselves are also differentiable. And that is what people call the model agnostic fine-tuning. So for over all our parameters, we're optimizing, we're checking how good can we optimize the new parameters there and give that as feedback to change our model. So mainly what you're doing is, if you're here, you're checking how easy can I fine-tune to the different models, and then you go in this direction. And how good this point is, you evaluate. Now you can't directly calculate that, but your loss function before would measure how good is this model. That is your normal loss function. Here your loss function is, okay, from here I do my 3 updates for the 3 tasks, I calculate then the loss, and then I can give this value, how big the loss at these 3 positions are, as a loss term here and back propagated then. So at every time step I measure is that are like, okay, when I take these values, how good do the later models get when I fine-tune them starting from this point? Is this a good starting point for my fine-tuning? And then you're hopefully ending up is exactly there. You're ending up at a position where it's hopefully easy to fine-tune a new model from. Any questions about that? Good. I hope you're not all gone by that, but hopefully got the main idea. I mean, not every formal equation here is important, but important is this idea with the thing is shown there quite good. That you're not optimizing the losses mainly. How easy can I learn a new task? Okay, so this is about the optimizing in the initial step. And there we now assume that in the second step, we do just normal fine-tuning. But maybe that is also not always the best. So maybe there's better ways than just doing normal fine-tuning, and that we want to look. My one motivation is, again, that we might want to do use an additional loss function. And we have done this somewhere very similar. Does anybody remember where we add some additional loss function to our weights?
Regularization.
Exactly. So we did there the regularization, and there we said our good model is mainly a model where everything is 0, because that was a bit our aim. We want to limit the complexity of the model. And now we have maybe a better estimation. We're saying, yeah, our initial model isn't bad. So maybe can you make changes? You're allowed to do changes, but try to learn a model which is good in your task, which minimizes your loss, but as a side constraint, which doesn't do too much changes. Again, the idea is, it should learn very specific things which are only happening here, which don't make any sense anymore. So just try to minimize the overall changes. And that is straightforward. We can do that exactly as the regularization. The only difference is now, we are not saying here the difference to 0. So we had here a 0 before there because it was mainly the absolute value at L1. Now we're saying no, that we're not saying that no model like the 0 model is the best, but here the best model is the original one. So minimize the changes to the original model, and that should then give you hopefully a good model that this only do limited changes. So we are trying to force the model to stay with the original model and only allow it to go away if that is really helping the loss function. So you're seeing now you have again the competition between your additional loss and your other loss. So you see that, if I want to change things, that has to improve my loss more than just the difference between that. So you have to have a significant amount of gains if you want to change the weights. And then again, so what it means is you're trying to learn what is really important and only to learn that and not learn just all the other things that can happen there. What you have now here, of course, is there might be parameters which are more or less important, or where it's more important to change them, and that is not addressed here. And therefore we have like then the next way of doing it, and that is called elastic weight consolidation. And that we at least want, again, to get the basic idea. We don't have to do all math about it, but again, the idea. Because the idea here is now, okay, on the one hand, we have an L2 norm, but the more important thing is what we now have here is we have somehow feature importance. And then you can also think that, can I learn the new things that's a different interpretation is, can I learn the new information in features which haven't been used before, because maybe then I'm not destroying what the model has done before. So I want to learn the new things somewhere where there's still space, where it's not destroying what I've understand before. But maybe, I mean, these models are very heavily over-parameterized, so maybe it's good to learn these things there and not destroy what I've done before. How does it work? You can calculate what is called the Fisher information matrix, which tries to measure that where there is important information, and that can be calculated by backpropagation on the initial data. So that is one challenge here, that you need access to the initial data, and then you see a bit how things should be changed here. So if you have, this is your new task, this is task B, the second one. If you're starting from here, you would try to go in the middle where the lowest point is. If you're going to the L2 norm, you wouldn't go too far, but a bit in this direction. The elastic weight decay now tries to tell you, in this direction, like for this model, everything is good. So it's not really clear whether there is like all the good solutions. So maybe the best solution is to go here, where we have a low value for the new task, but also a low value for the old task. So we are trying to change parameters which are not so important for the initial model. So we're not destroying the old model and keeping somehow its performance decently good. How that works is shown a bit here. So here we have from the original EWC paper, mainly the left two things here. So what you do is you first train on task A, then you train on task B, and then you train on task C. And in the end, you want to be, so you do 3 steps, and maybe you want to have overall good performance. So first, maybe let's have a look as S2D, so the baseline. That is a bit what you expect. So first here is the best performance when only training on A, and then you're going down. If you first train I and B, you're really unlearning things again. For B also, first you're learning that, then you're getting good, you're stable, but if you train now C, you're losing in that performance again. And the same thing is here happening for as to D for C, of course, you're getting the best performance. If you now do elastic weight decay, the interesting thing, what is happening is that you're, of course, still learning A and you're still learning B. You're not as good on the last task. So you're, of course, you have to pay a bit of a price. You're not finding the very best possible solution for C, because that might be a bit different, but you're staying reasonably good, and especially on tail task A, you're learning still, you're still doing very good on that. And you see, if you especially do a lot more tasks, so this is a single task performance, if you add more and more and more and more tasks, you're losing a bit, but you're not losing too much, where you see that if you just do normal continue fine training, you're more and more losing your initial performance. Another example of that is in automatic speech recognition, where we had this thing already before. So this was a vanilla model. I know it's a bit hard to try to explain it. So we start with 10 languages. We train a multilingual ASR system on these languages. And then we're afterwards adding new languages. We're doing all together, that is Oracle, so then we are very good. And we are better on the first ones because that are the high resource languages than the others. But it might be we can't always use all the data, or we can't just jointly train them, because first we only have that, and then the boss comes and, oh, I now want also have a ASR system for Romanian you didn't think of, and if you then have to retrain everything, that might not be very efficient. So what you then can do is, what we see, you could do elastic weight decay. So what you then do is, if you do elastic weight decay, you can do you get much better on them, but still very high, and you're not as good as the ones that you had before. What you then combine that is, you can combine that with weight factorization, and if you combine weight factorization with elastic weight decay, mainly meaning, okay, I allow for new parameters, and I even allow to change the old ones, but the old ones I only allow to change so that it doesn't disturb, then you get here performance which is very similar to the best one, as if you've trained everything from the beginning. Good. Any questions? Good. Then I think I was a bit fast today, so you have 10 minutes extra. Early holidays. What you should remember is, like, generally the idea of transfer learning, we're coming to that again. We looked at architectures, at training, and at fine-tuning data for that. And then otherwise, I wish you a nice week off, and see you again in the week afterwards.